on the variation of parameters. In the previous session, I established the fact that we can use the Cramer's rule to solve systems of equation. So in this video, it might be a bit long because I'm going to take examples on how to solve the VOPs in one section. So quickly, let me just do a simple system of equation. Like what I have in mind, slide 38. The equation is 2x plus y equals to negative 1. 4x plus 3y is equal to 1. This is a system of equation. If you're going to use substitution method, you realize that you're going to have a whole lot of variables playing around. The same with elimination method or with Gaussian elimination. And so I would like to use a Cramer's rule. Cramer's rule says that write your systems as matrices. So the unknown here is x and then y. And then the b part is negative 1, 1. The coefficient here becomes 2, 1, 4, 3. Now how do you solve this? For this, I can simply use Gaussian elimination. So I think my first comment wasn't right because it is constant here. But if I want to use a Cramer's rule, this one here is called the Wronskian. And we find the Wronskian such that it can be equal to 0 or it's not equal to 0. If it's equal to 0, we say that it is linearly dependent. And if it's not equal to 0, they are linearly independent. We expect them to be independent to have a solution. Okay. So this is how, if I want x part, I have to replace the first part of the equation or the coefficient by the b. So I have negative 1, 1, then the other ones remain over the Wronskian. In the same, if I want to find y, because y is the second variable, it means that I replace the second part with the b. And so I have 2, 4 remaining and then negative 1, 1 over the Wronskian. Wronskian now is the determinant of your 2 by 2. Don't forget your W is 1, 2, 4, 1, 3. The determinant here becomes 6 minus 4, which is 2. All these are determinants, so I can now find my x. This is the Wronskian W. X become the determinant for the numerator becomes negative 3 minus 1 all over 2. Y becomes 2, 1, 2 plus 4 all over 2. And then whatever solutions you get, these are your x and then y. This is how we use the Cramer's rule to find answers. Having said that, I will now take let's say 2 examples using VOP. And so the answers is negative 2 and 3. I hope that is correct. Example 1. So I'll take a new sheet here. We want to find general solution to a problem of the form y. It is second order. Okay. Now this is non-homogeneous. Because this is just exponential function, I can use MOU to solve it. I can use VOP. I should get the same answer. So I'm going to use a VOP. We first have to find the roots as usual. I don't want to go through that, so I'll quickly check my answer here. The root is 1 and then 2. It means my complementary solution is of this form. Okay, that is it. Now for VOPs, we say YP is a copy of YC. Don't mistaken this for MOU, which is a copy of the GT. So becomes U EX plus U2 E2X. Now with this solution, it is the same as having it this way. It means your Y1 is this part, your Y2 is that part. Now what is the order here? The order here is 2. It means I have to differentiate it n minus 1 times. That is just the first derivative of my y piece. So my system simply becomes the first state of my solution and then their first derivatives. That is all. The unknowns here are the u1 prime, u2 prime, which will be equal to the first term takes 0, the last term takes gt over a. So how would this be like? My y1 is e to the power x, y2 is e to the power 2x. Derivative. The first derivative here is still the same. The first derivative here becomes this, with the u1 prime and then u2 prime is equal to my right hand side 0. Now gt from the question is e to the power 3x. A is 1. The coefficient there is 1, so it remains as e to the power 3x. Now you see that for these examples we have variables, unlike the first thing I went through. Using the Cramer's rule, the Wronskian, this is the Wronskian. The determinant here, we are going to get 3x minus, this is a 2 by 2, e3x. Applying indices, you know, if I have exponential of a multiplying exponential of b, it is a plus b. So that is what I'm applying here. I'm going to simply get e to the power 3x as my Wronskian. So using the Cramer's rule, my u1 prime is simply some terms over the Wronskian. Because u1 prime is the first term, let me use a red pen. Because u1 prime is the first term, it would substitute this by the first terms. So it's going to be 0 e3x. Let me go back to my pen. Then this one's remains. Okay. In the same way, if I want u2 prime, it is some terms over the Wronskian. What are the terms? So I'll use the colors. Now because u2 is the second term, means I replace these ones by the terms here. So it takes 0 to e3x. And then the first terms remain. Now what do we get for the upper determinant here? It is this minus that. So I'm simply going to get negative e to the power 5x over e3x, which is simply negative that. The same way for this, I have this minus that. This is e, yeah. So I have e to the power 4x over 3x, and that simply gives me ex. Now don't forget that our yp is in u1 and then u2, so it means I have to integrate u1 term, and that will be integral of negative 2x dx. This is integration, it's no more derivative, so I simply get this as my answer. The same way u2 will be equated to the derivative, the integral of u2, and so I get integral of that is simply this. I hope I'm correct with the integration. Okay, so now what will be my final representation of yp? It was u1 ex plus u2 e2x. u1 is that, u2 is that. So a simple substitutions here. I hope this becomes easier to follow. I expand now. which is 3x here. You realize these are common terms, so I can simply have it as half of a3x. It's negative plus 1. Negative half plus 1. This is the same as negative half plus 1. Then the factorization comes out. And so this is it. Hence, I can write my final general solution, which is the complementary plus the particular solution. This is the final solution. It implies that if someone is using the MOU, we must get the same answer because it's a simple exponential function. I'll take 2 more examples and we'll be good to go. So I'm going through my slides. I'm done with the example 1. We've gone through all these things. Yeah, and then you see that's the final solution. Example 2. Now with this example, I have 4 to the second order again. Because of the nature of my GT, I can use MOU and I can use VOP. I must get the same answer, but we are using VOP. So what is the root here? You know, you have to first set these ones to, let me just do the right thing not to confuse you. So I have 4y prime prime minus 4y prime is equal to 0. This is my complementary part. Again, I'll just quickly go through my solution for the complementary. It means the root is lambda 1 is 2, lambda 2 is negative 1. You can verify these things. And so we have that. Now it's in terms of t's, it doesn't change anything. This is yc. VOP says that my yp should be a copy of the yc. So I have u1, this remains, u2, and then the other solution remains. So I'm done with this part. Now the question is, how do I get my system? Again, the highest order here is 2 from the question. The highest order here is 2. N minus 1 derivative times. It means I just have to find to the first derivative for my system. The system should be the y1, y2, and then its first derivative, such that I have u1, u2 prime should be equal to, the first term is 0. The last term always take the gt over a. So let's do the substitution quickly. So it means I have y1 is e to t, y2 e negative t. Now the first derivatives, the first one is 0. My gt here is 8 e negative t over a. With this question, my a is equal to 4. Don't forget over the a here, a is equal to 4, so I have to bring it. It's not just the gt, it is over a. Let me change the pen now. I'm done with this one, the system. Now I have to find the unknowns. What do? I'm going to use the Cramer's rule. And again, this is the Wronskian W. What would that be? AB minus that. So I have negative E T minus these two guys become 2E T. If I'm right, I can simply have this as negative 3ET. It is the determinant of 2 by 2 matrix. And so to find u1 prime, It is simply some determinant over the Wronskian. What are they? Again, because this is the first term, I replace this part of the equation by the right hand side. So 0, I can easily divide this to give me 2e negative t. Oh yeah, 4 to 8. And then the right hand side here remain. Quickly, determinant of this, you are going to have 2 of this, 0 over the Wronskian, negative 3et. And that will give me 2, e to the power 0 is 1. So I'm going to get 2 on 3 et. I hope my answer here is correct. So the Wronskian is correct. Yeah, I'm correct with this one too. Alright, so I have negative here because of AB minus BC. Then it would cater for this. In the same way, I can find the U2 prime as some determinant over the Wronskian. Again, because it's the second term, I replace this by the terms here. So the first one remains, and then I have 0 2e negative t. Determinant of this gives me that's over the Wronskian, and I'll simply have negative 2 on 3. Now I will address a question here. Someone will be wondering, how do I get the Wronskian to be exactly as probably the lecturer will have? Now it depends on the positions of your solutions. If I choose lambda 1 to be negative 1 instead, my Wronskian will be positive, and so that shouldn't be a problem. At the end of the day, you get the same answer. So how you position this one will determine how your Wronskian will look like. Please, so don't be scared of these ones. And so I can simply find my u1 as integral of that dt, and I can find u2 as integral of the u2 dt. These are integrations. I'm not sure what to do here, but integral of that I get the same 2 on 3 et, and integral of this I have negative 2 on 3 t. I always want to verify. Okay, and so that is what we have. And so my particular solution is u1 some e was my first root. I have to make a substitution back into this. u1 2 t plus u2 e negative t. u1 is 2 on 3 et times that. Please, when you are done, don't forget to do the substitutions. Okay, so I'm going to get 2 on 3 e3t minus 2 on 3 t e negative t. This is my particular solution, and so I add it up to the complementary to have the general thing. You can verify these things. If I'm wrong somewhere, you can correct me through the comment section, or when we meet physically we can go through that. Now the last example, I wouldn't solve through to the last. I'll just give the system. Let me just take a clean sheet here. The last example we have order 2, okay. Now this is a unique example. Because of this nature, I'm restricted to use the variation of parameters because of the nature of my GT. So I have the root as the complementary solution is, if we've gone through this one, that's why I'm not solving them. I expect you to be able to generate the complementary solutions. It means my particular will be of the form now. The order here is 2. It means my differentiation here will be just of the first derivative. I'll just help you write the system and then I'll end the session. So the system y1 is this, the second is that, the first derivative here is that u1 prime u2 prime 0. What is gt? Gt is x e x over a is 1. Again, this is the Wronskian. So if I want u1 prime, it is simply some determinant over the Wronskian. Again, what do? You replace the first terms by that. So 0 x e x, and then the other ones remain. If I want the second part of the solution, it's still some determinant over the Wronskian. With the second, I replace it by the terms here. So my first one remains, and then I have the 0 x e x. What do I get for the numerator here? I'm going to get x of 2x over the Wronskian. I didn't solve for the Wronskian, but let me check the solution here. The Wronskian is 3 e to the power x. You know how to get it. This is the determinant of some e negative 2x ex negative 2e, and then the last guy, it is ad minus bc. And that is what we have. Okay. Where did I get to? Alright, so the second part, if I'm to find a determinant here, I'm going to get this times that I have x e, that'll be positive x negative x over the Wronskian. You can simplify this if it's possible. And over here, so I can simplify this to get x on 3 because this one's cancelled out. And over here too, I have negative x on 3. If I should take the denominator up, I'll have a positive, that's 3x. And so if I want u1, it is simply integral of that. It's in terms of x, sorry. If I want u2, it is simply integral of the u2. And this is how you solve for the variation of parameters. The most important thing is to write your system out. Then you are good to go. So I have a question here. It says, solve this problem using both the MOU and then the VOP. You realize that for this example on slide 46, it is a simple exponential function. So whichever method I use, I should get the same answer. On this note, we are done with solving higher order linear differential equations with constant coefficients. The next sessions will be on when you have a variable coefficient. How do you deal with that? And so stay tuned for more videos.